solutions. So it's all about mixtures. We've talked about mixtures in chapter 1. We kind of talked about mixtures a little bit when thinking about when you mix polar and non-polar. So we've sort of talked about it even a little bit in chapter 7. But remember in this, if you have a solution, that's just a mixture. The highest concentration component is the solvent. And it doesn't matter if you're talking about all gases like the air in the room. So the air in the room is about 79% nitrogen, 21% oxygen, and then a whole lot of really small gas molecules. And so less than 1%, that's not less than 1% carbon dioxide, argon, water vapor. There's a little bit, trace amounts of neon. So very small amounts of other ones. But that means, what's the solvent? Out of this list, what is the solvent? The nitrogen, because it's in highest concentration. Okay, so this is the solvent. All of these are solutes. Under almost all conditions, liquid solutions, the solvent is what? Water, right? So if you have the sweet tea was the example that I gave you in lab. So you would have the pigments of the tea, the caffeine, the flavorings of the tea, and then you would have sugar. All those are solutes because they're all dissolved in water. So water is typically your most common liquid solvent. I would tell you that Bacardi 151 and Everclear, both of those are 151 proof, which means that it is what? What's its percent? Does anybody know what proof means? What is 100? What is 100% in proof? You don't know this? Huh? It's 200. 200 proof. 200 proof is 100% alcohol. Okay, so when they talk about proof, if you just take what the proof number is and half it, that tells you the percentage. So this would be 75.5% ethanol. Yeah. Most vodkas are 80 proof. So 80 proof is what percent? 40. So half of it. Okay, so most vodkas, 60% is water. 40% is ethanol, so water is the solvent. But for Bacardi and for Everclear, which is sort of like your moonshines, it's like solvent, that's the solvent. So ethanol is the solvent because you would only have 24.5% water. But for all body tissues and everything, for all intensive purposes, water is going to be your universal solvent because it's always found at higher concentration, higher amounts. Even if you're talking about a solid, a liquid, or a gas, okay, whatever's the higher amount in the compound, that makes it the solvent. So that's what I was telling in this. So like brass is an example. Brass is an example of a mixture where you have the solute zinc in a solvent metal copper. They're both solids. You have to heat them to a liquid, mix them together, and that brass doesn't tarnish as quickly as copper does, which is the reason why they make this mixture. So it just has a little bit better shine to it. So a true solution is really what you talk about when you think about a solution. True solutions have extremely small particles mix into the solvent. You can't see it. Dissolves completely. Homogeneous. Does not separate. You can't filter it out with just normal filtering methods. That's considered a true solution. So I think of a homogeneous mixture as a true solution. And small solutes help this to happen. So like when you made your salt solution in lab, so you measured out 10 grams of salt, put it in that 100 milliliter volume, mixed it up. When it was done, you couldn't see any salt crystals at all. Nothing settled out. It stayed completely mixed, and then we could use it in our osmosis and dialysis experiments. That's a true solution. But if you have a big solute molecule, they call that a colloid. So colloids have large particles, but they're still soluble in the solvent. So they still mix and stay mixed. Milk is an example. So milk has really big proteins in it. And also, if you buy milk that's not the fat-free skim milk, it has fat molecules that are dispersed in it, and they don't just separate out. So it stays uniform. But they're a colloid. So a colloid, you can think of it as it makes it thicker. So I think of examples of colloids like gravy. So when you add starch to the meat drippings in your pan, so you can add a little bit of flour. Usually you stir that flour up in a little bit of cold water because it'll disperse in the cold water better. But then you pour it into your boiling meat drippings and you continue to stir and stir and stir. Those really large starch molecules will dissolve, but they stay big. And that's the reason why gravy is thick. Same thing with egg whites. So like if you've ever picked up egg whites, they're sort of gooey, stringy. They have this thickness to them, and it's because they have really large particles that stay mixed together. Jello, a third example. So Jello is just collagen. It's really keratin that's been extracted, and it can be added to boiling water, and it liquefies, but it's a really big molecule. So I kind of like their picture. Colloids are really big. Kind of like our starch molecule that we did in the dialysis experiment, really large compared to like the little teeny tiny salts, the really small sugars. They're much bigger, but if they stay mixed, they're going to act as like a thickener. Suspensions, on the other hand, is when you have particles that are too big to stay mixed. So those you can take and shake it up, and you can get it to mix, but then it's going to settle out. So true solutions, this is like salt water. Very small solutes dissolved in water. They interact with water molecules. They stay mixed. They look homogeneous. You can't tell that they're even there. Like you couldn't tell distilled water from a salt water solution just from looking at them. They'd both be completely clear. But colloids, you're going to be able to tell because they're going to have a thicker consistency to them. They still stay homogeneous though. They still stay mixed. They still look uniform, but they don't settle out. And so this, proteins and egg whites. Suspensions though would be really large solutes that they don't have intermolecular attractions for the solvent. And so instead of staying mixed, they settle out. And so for the few that have did the lab today, those antacids. Okay, so not everybody. Some people's went really like, bing, oh, look, it's done. And other people are like, will this ever dissolve? Like over there stirring and stirring. And even after 20 minutes of stirring, there's like all these little particles settled to the bottom. Okay, they're like, it mixes if I mix. As soon as I stop stirring, it all settles out or it all comes up to the top. So that's a suspension because as long as you are mixing it, it stays mixed, but it doesn't actually dissolve. And it's really, it could be little particles. It's just that those particles don't interact with the solvent, and so they're going to separate out.
So kind of like Italian.
Okay, yeah. And so that one is because you have polar and nonpolar. And so that difference would cause them to separate. Or you have a solid that is more stable as a solid than it is mixing with water. And that's really what, like if you've ever eaten antacids, you know how chalky they taste? Okay, that's because they don't dissolve in your saliva. So it's sort of like you're chewing this like powdered up gritty stuff. So you have to like chase it with some water or something to try and get it down. But that's because those antacid salts are not soluble in water. They're actually more stable as a solid. So that's the challenge with them. So a good example of this one are a lot of medications, like amoxicillin. So amoxicillin, My kids loved it. They were always like excited. They would get sick and be like, I'm sick. But then they'd be like, well, you have to take amoxicillin. Because it was the pink bubblegum stuff. And they were like all about some pink bubblegum liquid. It was like made being sick not such a bad thing. So amoxicillin, though, if you look at it, it's called a suspension. So when you get it, if you take your prescription to the pharmacy, the pharmacist takes the bottle, and the bottle has this pink powder in it. And the powder has the medication plus all the flavorings in it. All he does is break the seal and add a certain amount of water. And it says right on the bottle, add 50 milliliters, shake thoroughly. So that's pretty much the pharmacist is like, okay, I can do that. And then passes it out to you. So that means, though, the amoxicillin doesn't dissolve in the water. But you make a suspension by shaking it, and you shake it well enough so that when you go to pour it, it's mixed long enough for you to be able to, for the kid to be able to swallow it. But if you let it sit, what does it do as it sits in the fridge? It separates back out. So if you pull it out, you can see there's the powdery stuff at the bottom and the liquid stuff on the top. So that's why you would end up having to mix it each time to make sure you're actually giving them an even amount of medication with each liquid volume. So blood. Blood is actually all three of these. So what are the biggest components in blood that are suspended in plasma? What are the largest components in blood? You can see them in the microscope. Mm-hmm. Yep. So red blood cells, white blood cells, and so they are so large, they're their own little individual particles or pieces. Why do they stay suspended? What is unique about the blood in your body? What is it always doing? It's always moving. Okay, so it's always moving and getting mixed up. That is why it doesn't automatically settle out. So this suspension, it stays mixed as the blood circulates. But it's also a colloid. So in plasma, the liquid portion of the blood, so roughly half of your blood is a liquid. The other half are these blood cells. It's like a 45-55 thing, but it's about 50%. So about 50% of your blood are these blood cells floating along, mixing constantly. The other half is this fluid. And so this fluid's kind of a yellowish looking, clear solution. And in it, it's kind of thick. And the reason it's thick is because there's proteins in it. Proteins, one of them is called albumin. Albumin helps to thicken the blood, and it also helps the blood to keep the right amount of water. So albumin is constantly produced by your liver and put into the blood, and it tries to maintain this sort of thickness to it. It helps with water balancing. So it keeps the right amount of water in the blood no matter what the conditions as the blood passes through all the different vessels, whether it's passing through the lungs or digestive tract. As it's passing through all the vessels that supply all the tissues, albumin helps to make sure that water stays in the blood so the blood stays liquid as it goes. So it's a big problem with people that have liver failure. So this is one of the major issues that comes into play with fluid balancing. So they start blowing all up, so they look like their abdomen is like huge and swollen. It's because they don't have any albumins. If their liver shuts down, they're not going to make those albumins. They're going to have a very difficult time with keeping fluid in the blood. Instead, it all collects in tissues. It all starts collecting in the body cavities. So we have a suspension, the blood cells. We have the colloid, these proteins that are found in the blood. But we also have the true solution. So what else is dissolved in plasma? Very, very small molecules. In the water of plasma, what dissolves? What's our transporter stuff? Talked about one yesterday or last time. One would be salts. Salts that are dissolved in the blood. What else is dissolved in the water of the blood? The nutrients, and we'll just lump them into nutrients because that could include amino acids, carbohydrates, could include lipids, although lipids are held by carriers. So remember the HDL and the LDL? Well, they're mixed in there too, and those are carried around. Waste molecules. The blood passes through the kidneys in order to allow for that filtration, something we're going to talk about in this chapter. Gases as well. What are the two main gases? Oxygen and carbon dioxide. Oxygen is brought in, carbon dioxide is on its way out. So the blood is actually all three. It has characteristics of all the different forms of solutions. And you can see in this one, this picture, so what they did is they took a sample of blood, and we actually did this like with milk, remember? So you put milk in the centrifuge and we spun it, and so the less dense fat came to the top. So they do the same thing. So if they collect a sample, a vial of blood from you, then they'll put it in the centrifuge and they can separate it. So that way they can see that slight yellow liquid, that is the plasma. And then down at the bottom, those packed, the dark colored, those are the red blood cells. This would be very concerning if I had a patient and this is what I saw. Why? What's really low? The red blood cells should be about half. So the first time I saw this picture, I was like, this person's like had major hemorrhage. They're super anemic because their packed red blood cells look like maybe 25 or 30%. So that's not such a good thing. But I don't know. That the chemist might not know that. It was very, very interesting. But that's one you can see, that mixture that's there. So you can change how well things dissolve. And we did this when we did the soap lab. I had to make a saturated solution of sodium chloride. And so in this first one, this is a unsaturated salt solution. So we just took sodium chloride and we added it in. And so you get sodium ions, those chloride ions, sodium ions, and the chloride ions. And I mixed it and it dissolved completely. So then I added more. So I get more sodium ions, more chloride ions, more sodium ions, more chloride ions, more sodium ions. Now eventually, I get to the point that the water molecules cannot surround any more sodium chloride molecules. Like the water molecules are just doing as much as they can to balance them out. When you get to that point, that is called saturated. So we can add until you get to this max. And that's saturated. So I always think of saturated as it just means there's as much solute as possible. If I add any more, it's just going to settle in the bottom. And that's actually how you know you have a saturated solution, because you just keep adding solutes until you can't add any more, and then you know the sample is saturated. But if I take this and I change the temperature, will it become, can I dissolve more or less if I raise the temperature? More, because you do that a lot when you're heating things. So you might put a little bit in and you stir it, but then you start to heat it and it all liquefies. Because by making those molecules move faster, they can actually hold more solute. So if I increase the temperature, I can increase the solubility. Same thing, remember when we made aspirin? So you added your water to your aspirin sample and you set it on ice. So what did that help to do? Cause the aspirin to do what? Right, then it started crystallizing. So you were sitting there stirring it, had it on ice. So we dropped the temperature and that lowered the solubility. So for solids, solid solutes, dissolving them in liquids, warming can help move molecules faster and improve dissolving. Cooling will help to move molecules slower and actually cause them to crystallize. As long as you kept your aspirin sample cold, it would stay crystallized. If you had warmed it, it would have all dissolved again. So all the little white crystals would have all disappeared and it would have just looked like a clear liquid again. Gases are different though. So if you heat a gas, or if you heat a sample that has gas molecules in it, those gas molecules want to leave the liquid at a higher rate. So because as they begin to move, instead of mixing better, they actually want to move completely out of. So if you increase the temperature, the solubility of a gas goes down. So that's actually the opposite of salts.
That's still kind of like the same concept, like you're heating the wine bottle or pops out.
Yes. So that begins to generate more gases, generating pressure, and that's enough to push it out. So I was going to bring soda, but I don't drink soda, and so I was like, well, I was going to go buy 2 sodas and put get one real cold and one warm. So if you're a soda drinker, you can try this. But if you open a bottle of like room temperature soda and just pour it in a glass, the bubbles are really big. So it'll form large bubbles because that's warm. If you take a cold, like refrigerator cold sample of soda and pop it and pour it, the bubbles are really fine. So they'll have really small bubbles, and it's because chilling will actually improve the solubility of the gas. Warming will actually decrease. So it's the opposite of solids. Solids dissolve better when you warm them. Gases lose their solubility when they're heated. So we can increase gas solubility by decreasing the temperature. And the exact opposite when you increase the temperature. So a little bit like backwards, solids dissolving in a liquid versus gases dissolving in a liquid. An application of solubility and pressure, because remember gases, pressure, volume, temperature, all end up affecting the behavior of gases, is Henry's law. So Henry studied gas solubility and pressure. So he was looking at how gas molecules and why gas molecules dissolve and how they stay mixed. What is the pressure difference to keep them there? He really helped to explain and understand why gas molecules have the ability to actually go from the air into your blood, going from a gas sort of surrounding and then dissolving into a liquid environment. So when you breathe in, we said you have about 21% of oxygen, right? That's like the percent of oxygen in the air. So when you breathe in oxygen, you also breathe in nitrogen, you breathe in some of the carbon dioxide and water, all the other gas molecules go in, but the oxygen it has a pressure within the air sacs of the alveoli, just like the air pressure. Well, it has alveolar pressure, and its pressure of that fresh oxygen coming into the air sacs of the lungs, and you can think of them as being kind of like the very end tubes within the lungs. The pressure is about 100 millimeters of mercury. But in your blood, the pressure of oxygen coming right past these little air sacs is really low, only about 40%. And so this is where you get a difference in pressure. So Henry said, gases like to go from where they're at high pressure to where they're at low pressure. Solubility improves moving from high pressure areas to low pressure areas, and the goal is to do what? Balance them, right? So here we have 100 millimeters of mercury of oxygen pressure, only 40 in the blood. And that is the force that causes causes oxygen to actually dissolve into the blood for transport. So the difference in the pressures is the reason that oxygen moves in. If you look at carbon dioxide, though, notice that carbon dioxide, it's a little higher in the blood. So it's about 45 millimeters of mercury in the blood and only 40 in the air sacs. The reason that it's so high in the air sacs is because you don't ever exhale all of your air. So even when you go and push it all out, there's still a little bit of like non-exhaled air. So that's why it's that much in the air sacs. But it's still enough of a difference. 45 millimeters of mercury, 40. That is enough of a push to promote the movement of carbon dioxide out of the blood and into your air sacs. So inhaling allows oxygen to increase in the air sacs, moves that oxygen into the blood. Carbon dioxide is going the exact opposite direction. So they're just moving from high concentration to low concentration to try and balance those concentrations out. And then when you exhale, you get rid of that excess carbon dioxide and then you bring more oxygen back in. And that's really the whole reason you have the whole trip to the lungs is for that pressure differences. So this one kind of shows this movement that occurs. So this oxygen, this pressure moves oxygen in, carbon dioxide gets moved out of the blood and into the air sacs. And with the goal of bringing that oxygen level up until those pressures are balanced. So another sort of property of things dissolving and things mixing is what happens to the individual solute molecules when they mix. So when solutes dissolve in a solvent, the nature of the solute may affect what the solution is actually capable of doing. So they characterized compounds that have the ability to form ions from compounds that don't. So when you take a solute and you dissolve it in a solvent, and for us, we'll just talk about water, okay? So that you can characterize what does that solute do? Does it just dissolve completely or does it actually separate and form ions? So for example, with sodium chloride. So you know sodium chloride is a solid. If you have a sample of water and you put a spoonful of salt in, stir it up, completely dissolves. So that means that it hydrates. So it's going to mix completely with the water. But the sodium ions don't stay connected. The sodium ions, they interact with oxygen in the water. Chloride ions interact with the hydrogen of the water, and they can like separate and float around each other. So you end up with sodium ions. These are now called aqueous. AQ indicates that they're free floating, not stuck to the chlorine anymore. And you get chloride ions. These are also aqueous. Well, ions are capable of carrying an electric current. And so the terminology came about that they were electrolytes. To demonstrate the presence of an electrolyte or not in a solution, I've made up a couple of beakers. So this first beaker is a beaker of distilled water. So I have this light bulb. The light bulb is plugged in. If there were ions in solution, it would be capable of carrying the current and would cause the light bulb to light up. But since it doesn't have any ions, there's no electrolytes currently in, it doesn't. So I'm going to add just a little bit of sodium chloride. Stir it up just a bit. The sodium chloride, we said, is a strong electrolyte. As long as it's an unsaturated solution, the sodium chloride will dissociate 100% and form many ions. These ions now have the ability to carry the current between the two black electrodes at the bottom of the light bulb, completing the circuit so that electricity can flow. So now I'm just going to rinse them. You see rinsing them in water, there is no response. Now, what if I use something like sucrose? Sucrose is table sugar. I'm going to put a little bit of sucrose in this beaker. Just stir it up. Sucrose is table sugar. It is polar. It's a covalent molecule. Sucrose does have the ability to dissolve. It is a soluble solute in water. But when sucrose dissolves, it does not break into ions. Instead, because it is polar, it has the ability to interact with the water molecules, but it does not form ions. And so you see that it does not conduct electricity. So sucrose is considered a non-electrolyte. I have another sample to show you. This is ethyl alcohol or ethanol. So alcohol in solution. If I put this, you notice this as well. Ethanol does not form ions in solution. It is also polar, but it does not dissociate in water or form ions, so it is also considered a non-electrolyte. The last one that I have to show you, though, is vinegar, which is acetic acid. So I put some vinegar in a beaker. Vinegar has the ability to dissociate partially. This is an example of a weak electrolyte. And you notice that it barely makes the light bulb glow. Because it only forms about 10% ions, most of the vinegar molecules remain associated and can't conduct an electric current, but very small amounts of them have the ability to do that. So that demonstrates the ways to tell strong and weak electrolytes apart. So in these, you can have like 3 different types of hydration reactions that can occur. So if it's a strong electrolyte, you know that the light bulb is going to be super bright. A strong electrolyte, all the products will be aqueous and you'll have ions. So I kind of wrote it down like, okay, here's the steps that you do with each one. So if the arrow, with a strong electrolyte, the arrow will go just to the right because 100% goes and becomes ions. What you do is you just separate the component into its individual ions, positive and negative, and just make sure that they're balanced. So in this one, HCl, when this is added to water, I end up with H+, which is aqueous, and Cl-, which is aqueous. And you see that it's already balanced. 1 hydrogen on either side, 1 chlorine on either side. Now with Fe2O3, I put this in water and get it to dissolve. Then I'll end up with Fe. The charge on that, if you remember how to figure out the charge, you like back, whatever the coefficients are, tells you the charge. So the 3 oxygens tells me that it's a +3 charge, and the 2 irons tells me that oxygen has a -2. Or you could just look because it's in group 6. These are still, both would be aqueous. Aqueous. Now, if I wanted to balance this, how many irons would I have to have on the product side? If I have Fe2O3 on the reactant side, how many iron ions would I have to have? 2. So 2, if it's Fe2, means there's 2 irons in the reactant. So I'd have to have 2 iron ions in the product. So that way that balances them. What about the oxygen? You'd have to have 3. So I have 3 oxygens here. That means I'd have to have 3 oxygen ions. So that way that accounts for how many? 2 irons, 2 irons, 3 oxygens, 3 oxygens on both sides. Now a weak electrolyte is different because a weak electrolyte doesn't dissociate completely. It only dissociates some. And so in that, you want to use a double arrow. So rather than just having an arrow go one direction, which you know means 100%, you have the double arrow. You still separate them into ions because it's a weak electrolyte, but it still does form ions. So Na2CO3, what would I make? If you split this, Na plus, right? And sodium's in that first column, so it would be just a positive 1 charge. And then CO3. CO3 is that carbonate. What's its charge? It's going to be negative. It's balanced with the sodium. So if the sodium's 2 of them, what's the charge on the carbonate? -2. These are also both aqueous. Aqueous. How many sodiums would I need in the product side? So I'd have, see how I have 2 sodiums here? That means I'd have 2 sodium ions. When it would split up, so as a reactant, there'd be 2 sodiums to 1 carbonate, but when it dissolves, I end up with 2 sodiums and then just 1 carbonate. When that molecule splits up, it forms ions. So hydrogen fluoride, HF, is another one. It's a weak acid. It can separate, but it doesn't do it 100%. So what are the ions that it forms? If HF splits. Yep, and H would be positively charged, and fluoride, which would be negatively charged. So they just split into ions. They would both be AQ. And I wouldn't expect you to know if it's a strong or a weak electrolyte. I would tell you. So if I gave you this, if I asked you this, I would say finish the reaction for HF, which is a weak electrolyte. So you would know to put the double arrow going both directions. Just separate them into a positive and a negative ion group and just make sure they're balanced. So are they balanced this way? 1 hydrogen, 1 hydrogen, 1 fluorine, and 1 fluorine? So these would just all need 1. They wouldn't change because all you would do is just separate the HF into individual hydrogen ions and fluoride ions. Now the difference if it's a non-electrolyte. A non-electrolyte, you use a single arrow like you do with the strong electrolyte, but with the non-electrolyte, there's no ions. Yeah, so all you have to do is just write the reactant again, exactly as it is. So this is ethanol, CH3CH2OH. That's the one that we looked at. And instead of being a liquid, what would it be? Just means it's dissolved in water. So aqueous just means it's mixed in water. So you notice there, the reactant and the product don't change. They're not going to change. And you don't have to worry about balancing it because you take one of these and it becomes one of those. Just mixes with water. But it's because it's polar, it can do that. So same thing, sucrose, table sugar. The only difference, table sugar is a solid. When you mix it in water, it becomes aqueous. So it dissolves, but it's still a 1-to-1 thing. Until you get to the point that it is a saturated solution, it's still the same. So follow those steps in each one to be able to determine those differences between them. When looking at ionic solutions, they will oftentimes talk about equivalence. So they'll use the term EQ. An equivalent is really the same as the amount, talking about it in terms of that counting number. Remember we talked about moles. Equivalents are really the same, except it includes the effect that charge has. So if you have 1 mole of sodium ions, that would be 1 equivalent. And it's because sodium has a +1 charge, so doesn't change the ratio. But if you have 1 mole of calcium, because the calcium has a +2 charge, that will affect the relative positive and negative charges that you have in solution. So that would be 2 equivalents. More commonly, you will see them listed as milli-EQ. And they will oftentimes, when they run blood panels to look at sodium levels, they talk about milli-equivalents. in terms of amounts of sodium or the amounts of potassium, they're really talking about like numbers of moles, because equivalence is really the same thing as moles, except that equivalence is related to the charge on those ions too. Electrolytes are what you find in blood, and all it is just the ions. It's just the salts. So you have sodium ions, potassium ions, chloride ions. And we talked about these a little bit in ionic compounds. Sodium being really important in nerve impulses and water balancing. Potassium playing a role in nerve impulses as well, and muscle stimulation. Remember, that's when you eat bananas if you get a lot of leg cramps. Calcium balances all the positive ions. But when they look at total ion concentration, they want the total number of positive ions and the total number of negative ions to balance. And under most conditions, they do. Because if you make a solution of sodium chloride, it's going to have equal amounts of sodium and chloride ions and equal amounts of positive and negative. So when they give solutions, they look at amounts of the ions that are present. If they use saline, physiological saline is 0.9% sodium chloride. They call it physiological because that is the normal salt condition in the blood. 0.9% sodium chloride, pretty small, but it has sodium and chloride ions about 150, which is sort of the normal balance. So if a patient's sodium levels begin to get very high, then that's going to affect their water balance. That can also begin to affect nerve impulses. So if excessive amounts of sodium or potassium or lack of any of these ions come into play, that can affect normal functioning. So the second one, the potassium chloride. Potassium chloride is oftentimes given in addition to regular IV solutions. Have anybody ever had that, like a potassium like piggybacked on? Why would they do that? What patients tended to need that? Not just malnourished, but most of the time, these are the sort of chronic disease patients that have been in the hospital for a while, because under those conditions, their body is in stress mode. And so when you're in stress mode, your adrenal glands are like running the show. Your adrenal glands are trying to raise your blood sugar. Your adrenal glands are trying to raise your blood pressure. They're trying to maintain electrolytes, so like holding everything. The problem is that you can actually end up losing potassium this way. So in order for your kidneys to try and hold blood volume, they're going to hold sodium, but they're going to do it at the expense of potassium. So that is why patients that have chronic disease and are really having they're having sort of loss of regular responses, oftentimes potassium levels are getting too low. And if potassium levels get really low, that'll cause the heart to begin to beat irregularly. So they'll monitor, look at potassium levels, and then give them to try and bring that back up. So it can cause the heartbeat to weaken. And it's really the response to chronic stress. Not like short-term stress, but like the long-term stress. Patients that have like kidney failure, patients that have other internal diseases that are not being balanced out, and that can end up being the side effect. Some of the other ones, if you look at them though, you see that the positives and the negatives pretty much balance each other out, whether you're talking about replacing fluid when someone's dehydrated, or if you're giving them this maintenance. They oftentimes do it, they'll call it like a D5W. So that's dextrose, 5% in water. So that's trying to give that sugar solution. So the goal is to try and bring those into a balance. So we've talked about nutrients like blood sugar in milligrams per deciliter. So that is the amount of a solute in a solution. Blood proteins are oftentimes described in terms of grams of protein per deciliter of blood. But these are all looking at concentrations. So in concentrations, one of the more common ones is the term molarity. So molarity is how many moles of a solute you have per liter of a solution. So they use a capital M. So every time you see a capital M, like in lab today, we used a 0.1 molar solution. So it was 0.1 with this capital M, then HCl after it. That's 0.1 molar HCl. And this means there is 0.1 moles of HCl per 1 liter of the solution. This is just sort of like an abbreviated way to try and talk about a concentration. You can solve problems in molarity. You can figure out how many moles of a sample you have. You could figure out how many grams of a solute is present by being able to just do a conversion from one to the other. It just adds in this volume aspect because it's in a solution rather than just being individual like a pure substance. It's adding it into a water solution, so you have to take that volume into account. So my example is when we made soap. So you had to use a 6 molar sodium hydroxide solution. So that was the lye. So I put that in the fume hood. So you had to go get 40 mils of that. You mixed it with 40 mils of ethanol, and that's what you added to your fat as you heated and stirred for eternity. But that means that you mixed these two. So if you know a concentration and you know the volume, you can figure out your solute just by getting those units to cancel. So 6 moles per liter is what 6 molar means. That's sodium hydroxide. We used 40 mils, but in order to be able to use the volume, you've got to make sure that units are the same. So notice here I have liters, but in my number I have milliliters. So I have to take and convert this to liters to be able to use volumes and get your units to cancel. To go from here to here, 40 milliliters times in the line, there's 1,000 milliliters in 1 liter. So in this one, milliliters and milliliters will cancel. 40 divided by 1,000 is 0.04. Decimal place just goes 3 places to the left. Just remember, and this is just pretty much, you'll just have a single unit conversion. You don't have to do any more than that. So now I know how much of that sodium hydroxide I have. So if I multiply it times the volume, what happens to the units here? So liters and liters will cancel. So you can take the concentration times the volume. You have to make sure the units are correct. Like make sure that they're the same units. You can't use milliliters and liters directly. You've got to make sure that you do the conversion. But you can do this, multiply concentration times the volume, and that will allow you to figure out how much of that solute you had. So 6 times 0.04 would be 0.24 moles of sodium hydroxide. From this, I can figure out how many grams this is. Because remember, to go from moles to grams, what do I use? So 0.24 moles is equal to how many grams of NaOH? What do I have to use to go from moles to grams? No, that's moles and molecules. You're thinking the exact right place. What do you need to know? You have to take the mass of each of those atoms in the formula and add them up. That formula mass. So the formula mass, and I didn't bring my periodic tables, 23 is sodium, just round to a whole number. So Na is 23, oxygen is 16, hydrogen is 1. So oxygen is 15.99, so we just round to 16. 22.99 for sodium, round to 23. Hydrogen's just 1, so adding those up, it is 40. So there is 40 grams in 1 mole. That's the formula mass. So I can use that, 0.24 moles times 1 mole, 40 grams. 0.24 times 40. Moles and moles will cancel. I do have some. I got 9.6? Yes? So we could have also taken and weighed out 9.6 grams of solid sodium hydroxide, mixed that with our fat, but by making a solution, it allows that reaction to occur in a liquid instead of having that solid mixed in, and so the reaction takes place better. It's a sort of a more even reaction. So in each one, always try to figure out, okay, what do I have and what do I want to know? Do I have all my units in the same form? Are my volumes the same so that they can cancel? And then in solving, you should see that units cancel as you go through. So I got that one. Another way that you can do a concentration is looking at percents. So percents, when we made that salt solution in lab, we made a 10% sodium chloride solution. So that means we took 10 grams of sodium chloride and we put it in 100 mils of the solution. So you went to the balance, you weighed out your 10 grams of sodium chloride, you put it in the graduated cylinder and had the volume at 100, covered it up, shook it back and forth. When it was completely dissolved, that's a 10% solution. Do you know exactly how much water is in there? No, okay? Because you just add enough water so that the whole volume is 100 milliliters. So you don't, this isn't saying 100 milliliters of water. You really don't know the exact amount of water. You just know you have to add enough water to give you the volume that you want. So in this question, if you have 23% of glucose in a 200 ml solution, how much glucose did you use? So this is kind of like solving a molarity problem, except whenever you see percent, just change percent to grams per 100 ml. So like change the percent sign, pull that out, and put in grams per 100 ml. Just like if you see the molarity sign, you change it to moles per liter of solution. So that sort of shorthand or the abbreviation, when you see this, just change it to its real form, like what it's actually telling you. So 23% means what? 23 grams per 100 ml. Just drop the percent part and add in what the meaning of percent is. But I didn't make 100 mils, I made 200 mils. So if you multiply it times the volume, milliliters and milliliters are the same. So you don't have to do any kind of unit conversion. These will just cancel out. Multiply everything across the top, divide by anything in the bottom. To be 46 grams of glucose. And just like how you made your salt solution, you put 46 grams of glucose in a graduated cylinder with markings up to 200 milliliters. You add enough water to make it 200 milliliters. So if you want to make a 12% sodium chloride solution with a volume of 600 milliliters, how much sodium chloride do you need?
72.
Okay, so you did this by doing what?
12 and 12 grams.
Mm-hmm.
600 milliliters.
Yeah. It's just a matter of taking your percent, convert it to what it's telling you. Percent is grams per 100 mils, and multiplying it. Milliliters and milliliters, same units, so you can do that without any kind of problem. So it would be 72 grams of salt. How much water will you use? Do you know?
No.
No. So all you have to say is enough. I will use enough to make 600 milliliters. Okay? If I added 600 milliliters, what would happen to the volume? It would be above 600 because there's going to be salt in there. That takes up room too. So you have, and this is like, I always get people with this question because I always ask a question like this. And people always like try to calculate it. You can't calculate it. Okay? All you know is you have to add enough water to make 600 milliliters with that 72 grams of sodium chloride in there. Because when you're talking about that 100 mils, that's the solution, not the solvent. So if I have a 2.5 molar sodium chloride solution in a volume of 750 milliliters, how many grams would this be? So I want to know how many grams. And here's what I know. When you see percent, change it to grams per 100 mils. When you see the big M, change that to moles per liter. So just take the capital M out and put in what it really is telling you or what it really means. So you have 2.5 moles per liter. But I need to know how many moles. I need to know how many moles I have. So what do I have to do next? I need to multiply it times the volume part. This should be 750.
Oh.
Sorry, it looks like an 8. It's just my scribbling. So I need to use this volume, but I can't use the volume in milliliters. I've got to convert it to liters. So I need liters because liters and liters then will cancel in the math. So that's really the only time you might see that you have to do a unit conversion. If you have liters and milliliters, it's a single unit conversion. 750 milliliters, milliliters on the bottom. Milli always gets 1,000. Liters would get the 1. Milliliters and milliliters cancel. Decimal place goes to the left, 3, so it would be not 7.5. So 0.75 liters. Liters and liters will cancel. That's going to give me moles. So the molar concentration times the volume will tell you moles. 2.5.
1.9.
So 1.875. So if we use 2, it'd be 1.9. So I'm not quite there. I have one more step to do. The first one is just figuring out how much of the solute you have, but then I want to know how many grams of that. So 1.9 moles of NaCl is equal to how many grams? To find this, I need to know what the formula mass is. So we said sodium weighs what? 23. And then chlorine's an oddball because chlorine's 35.45, so we would round down to 35. So this one would be 58 grams in 1 mole. So it's just a single unit conversion from there. So what goes on the bottom? Moles goes on the bottom, grams goes on the top, so you get 58 in 1. I got 110.2 grams. So if I was going to round that, it would be 110. So that's how much solute is in that solution. So first step would be just find moles. Second step is just converting moles to grams. So it's sort of like a two-step process in that one. So if you're going the other way, if you have an amount and you have a volume and you want to know what the molar concentration is. So we got to do this one backwards. What do we got to do first then? Other way, we have grams. So now we want to go. So in this one, we want to convert the amount of grams of sodium chloride, not that many M's, grams to moles. And then in the second one, then you just take the number of moles and divide it by the volume, because that puts it back in its molar concentration. So we said it's NaCl. So we just did this one. NaCl, we said there's 58. So we can use that 58 that we just figured out. So we have 88 grams of sodium chloride. Times in a line. What goes on the bottom in the first one? Grams is going to go on the bottom. Moles is going to go on the top. It's just a single unit conversion. You just have to do the one, so grams and grams will cancel. So we said there's 58 grams in 1 mole. Grams and grams will cancel. I got 1.517241379, which then, since it's 88, we would just keep 1.5. Okay, so we go from grams to moles, and now I want to figure out the concentration, so I have to take 1.5 moles divided by what? The volume. And nicely, it's in liters. Because in order to do capital M, that's moles per liter. So you take the amount of the moles of the solute divided by the total volume. This is the volume of the solution. And it always needs to be in liters. And really, if you kept it at significant figures, you would want to keep it with 2.0, right? Because there's 2 significant figures in each of these. Like on here, I have a couple more parts per million, parts per billions. I have a couple of practice ones, and then we'll talk about dilutions, and we'll be able to finish up chapter 8 with a talk about filtration, osmosis, and diffusion. Yeah, so we have all of these ones. So we'll do these ones next time and then finish up chapter 8. I won't see you Monday. Don't forget.